which has a classical chaotic counterpart. And there are two central conjectures. One is by Berry and Haber. They state that the spectral properties of a generic quantum system with a classically integrable counterpart behave like random numbers from a Poissonian process. On the other hand, if you have a system which is classically chaotic, then the spectral properties were predicted by Boigas, Giannoni, Schmidt, and independently by Michael Berry and Giulio Casati to coincide with those of random matrices from the Gaussian ensembles. These random matrices are Gaussian distributed random numbers, have them as entries, and if you have a system with preserved time reverse invariance, then they belong to the orthogonal universality class, and this is called the Gaussian orthogonal ensemble. If time reversal invariance is violated, then they belong to the Gaussian unitary ensemble, and there's a third universality class. This is a symplectic universality class. This is applicable to quantum systems which have spin 1/2 and correspond classically to a chaotic dynamics. So next slide. Yeah, so the statistical measures which are studied in this connection are the distributions of the spacing between adjacent eigenvalues. So before you can do it, you have to unfold the eigenvalues such that the average spacing is equal to 1. And then you find completely different distributions for the real spacings. For the integrable system, it's a Poissonian distribution with e to the minus s. It's just e to the minus s. In a chaotic system, the distributions all decay Gaussian-like for large spacings, whereas for small s, for time reverse invariant system, they go linearly with spacing. For time reverse violated system, they go quadratically, and for a system with symplectic symmetry, they go with power s to the power 4. So this already gives you one aspect which tells you whether your system is regular or chaotic. So if you find spacing, a distribution which is 0 as spacing d is 0, then this indicates that your system is chaotic. Other properties are the number variance, which gives information on long-range correlations, or, I will also show the results for Dyson-Meter statistics, which just gives information on the stiffness of your spectrum. If the eigenvalues are completely uncorrelated, as is Poissonian distributed, then it's not a stiff spectrum. So next slide. So, and I will present results for quantum graph. So quantum graph is a very simple system. It consists of vertices that are connected by lines. And on these lines, you have the one-dimensional Schrödinger equation, and the solutions are given in terms of a sum of plane waves. And if you, for a system, to obtain a system with violated time reverse invariance, you just introduce a magnetic field potential Aij. So for 0 Aij, you have a time reverse invariant system, and if you turn it on, then you have a system with completely violated time reverse invariance. And if you choose the length of these bonds, all incommensurate with respect to each other, then you can generate a chaotic dynamic, and you get the wave dynamics shows exactly the same properties as a system with a classically chaotic counterpart. So therefore we use such graphs to investigate the properties of quantum systems with a chaotic counterpart. Next slide. So, and this was too fast. So, the quantum part is first of all characterized by the vorticity, the valency on each of the vertices, that is how many of the bonds vertex is connected, and secondly, the length should be incommensurate, and then another characteristic are the boundary conditions at each of these vertices. So one boundary condition which has to be fulfilled is continuity, that all the wave functions should take the same values at a given vertex. Furthermore, you have the current conservation. This is the second one, and from this current conservation you can get a vertex transport of waves from one bond to another one via a vertex. And then you have a parameter lambda I for on each of these vertices. You can define boundary conditions, Dirichlet boundary condition. That is that the wave function vanishes, or wave functions vanish on a vertex would mean that the vertex is not connected to the graph essentially, and then you get a system with, which has the properties of an integral dynamics. On the other hand, if you choose Neumann boundary conditions, which would correspond to lambda I equal to 0, then you get a quantum graph with time reversal invariance and the properties of the chaotic system. And the vertex scattering matrix is a very simple one, which does not depend on the wave number k. Next slide. So, and for this case, where you just impose boundary conditions on each of the vertices, you can derive an explicit expression for the eigenvalue equation. And then wave functions are simple plane waves that have to fulfill continuity condition on each of the vertices. That is, the values should be phi I and at a vertex I. For all wave functions that are connected to vertex I, the values should be phi I at the location of at the vertex. And then you can plug this solution ansatz into the current conservation, then you get a secular equation which is given in terms of the determinant of a matrix. And this matrix has non-trivial solutions for the wave number k, only if this determinant is equal to 0. And this equation one can use to get the eigenvalues and wave functions of a quantum graph, which is described by the valency matrix and the boundary conditions on each of these vertices. That is, this is the way how I obtain the numerical results for eigenvalues. So now my talk vanished. So next slide. This is one possibility, that you give the valencies at each of the vertices and give boundary conditions in terms of these parameters lambda I. Another possibility is to give the transport properties of waves entering vertex I. So here I show for an example vertex 3 types of vertices with valency 4. That is, each of the vertices is connected to 4 bonds. And in the simplest case, which I showed before, a wave entering at entrance 1, for example, can exit at all other exits with the same probability. This would be the first example. If you want to create a quantum graph with GUE statistics, that is with violent time reversal invariance, then you use so-called circulators which give a direction to the waves. So in this example, for example, when you have a wave which enters at 1, it can only exit at 2. A wave entering at 2 can only exit at 3. A wave entering at 3 can only exit at 4, and so on. So you get a directionality. And the unidirectional graph is the third example, where waves can enter at 1 and 2, but only exit at 3 and 4, or they enter at 3 and 4 and can only exit at 1 and 2. This would be used. I will come also to unidirectional graphs, and there you have waves that only can move in one direction on a microwave network. To get the vortex scattering matrix, one has now to use the requirement that the Hamiltonian of the quantum graph should be fulfill self-adjointness, and then you get a vertex scattering matrix. And for the second example, which is essentially, this is called circulator, you get a k-dependent vertex scattering matrix. In the other cases, it's k-independent. So that's in the first and the last one. So next slide. So if you now don't give the value of lambda, so bond boundary conditions, but if you give conditions on each of the vertices, then you can also obtain the eigenvalues. In this case, you have to use the bond scattering matrix. So to obtain a scattering system, you just couple your quantum graph at 2 vertices to the exterior by attaching leads which extend to infinity, and then you have a scattering system. For the scattering system, you can compute the scattering matrix. matrix, which in this case would describe scattering between these green lines. So from the vertex attached to one green line to the vertex attached to the other one. This can be considered as a scattering system. Also, the matrix elements are very simple. They contain the vertex scattering matrix, and along the bonds you have a plane wave, which like e to the I k Lij. So this is again a very simple matrix. You can use it to obtain the eigenvalues by solving the secular equation that the determinant of 1 minus the scattering matrix should be equal to 0. This is standard scattering secular equation when you use scattering matrix approach to obtain the eigenvalues of your system. Then of course you have to make sure that the system is only slightly open, otherwise you get a dissipative system. And one advantage of these quantum graphs is that you can get an exact result for the semi-classical approach, that is for when you go with wave number to infinity, then you have an exact result for the spectral density. So the fluctuating part of the spectral density can be given in terms of the sum over these cosine functions. So this doesn't work. So like it's written here, and the entries are, they depend only on the valency of the vertex. Next slide. So in the experiment, in one type of experiments, we simulate quantum graphs using microwave networks. These are just coax cables which are connected by joints like the ones which I showed before. I mean, in a coax cable you have a center line which is and the outer, a cylinder. So, and they are, the medium between the inner line and the outer one is made from some dielectric medium, and you can write down the so-called telegraph equations which describes the potential difference between the inner boundary and the outer one, so the inner conductor and the outer conductor. This one, okay. Okay. I don't think it works because of the screen. Screen is too bright. So I would need a stick, but there's no stick. So I can do like this. So this is, then you get the telegraph equation. It describes how the potential difference along a coax cable. And you can also formulate, they also fulfill the current conservation. So it's similar to the result which I wrote down for quantum graph, and you have the continuity equation is fulfilled as long as the coax cables are well attached to the joints. Then you have again the continuity equation, you have the current equation, and the wave equation is similar to that of the quantum graph. So the Schrödinger equation, one-dimensional Schrödinger equation. So you can use such microwave networks to simulate quantum graphs because, as I showed in the next few graphs, next slide. I mean the wave equation, so the telegraph equation for microwave networks is mathematically identical to the Schrödinger, one-dimensional Schrödinger equation of a quantum graph. And the boundary conditions in a microwave network, so the properties of the microwaves are similar, exactly the same as for a quantum graph with Neumann boundary conditions. This is exactly the case where we obtain a chaotic quantum graph with the properties of a chaotic system, essentially. So, and this analogy holds below a certain frequency, because when you come beyond that frequency, you don't have these transversal electromagnetic waves anymore in a coax cable. And a good thing about quantum graphs is that the spectral density is simply a constant. That is, in this case, it's very easy to unfold the eigenfrequencies to a mean value 1, which you would need to if you want to compare with quantum matrix theory. Next slide. So here I just show one result. I mean, to obtain the eigenfrequencies of a quantum graph, you have to attach antennas to it and measure the transmission and reflection spectra. Here I show a measured one, which is in wet, and compare it to a computed one. So as long as the frequency is not too high, you find a very good agreement between both. But I mean, our goal was not to simulate exactly a quantum graph, but to simulate the spectral properties of it and the properties of the wave functions. So therefore, it's an ideal system to do such studies. And also, another advantage of these quantum graphs is that, I mean, by attaching antennas to it, you essentially open it. It corresponds to attaching leads to your quantum graph. And then you have an open scattering system, and then you can also investigate properties of quantum chaotic scattering system. That's what I also will show some results. Next slide. So here I show one example. So the white part shows such a quantum graph microwave network. So it's made from coax cables, and it has 4 phasors. And here I show an example which simulates a quantum graph with symplectic symmetry. So it's described by quadrant-Young real matrices. So it consists of 2 parts. Each of these parts is the same as a GUE quantum graph. That is a quantum graph where time inverse invariance is completely violated. And they are connected via 2 lines. And on these 2 lines, you need a relative phase of pi. And then you obtain a quantum graph which has a symplectic, belongs to the symplectic universality class. So this was the first time that such a symplectic system with symplectic symmetry was realized experimentally. And the idea was from Martin Sieber and Chris Joyner and Sebastian Müller, essentially. And it was first done in an experiment in Nice, essentially. They were the first, and we took over their idea and did several other experiments. I just will show some of that. Next slide. So here I show results for the spectral properties. Experimental results are the red point dots, and the black lines are the predictions from random matrix theory. In the left part I show results for a GUE graph, which is obtained by just taking 1/2 of the GSE graph, and the right one shows the results for a GSE graph. And as one can see, for nearest neighbor spacing distribution and integrated nearest neighbor spacing distribution, they agree very well with random matrix theory predictions, whereas for the long-range correlations, so number variance and this beta-Dyson statistics, one always finds deviations in a quantum graph. And these have to do with one of the drawbacks of quantum graph, and this is the non-universal properties. So in these you have backscattering at the vertices. So just to explain, next slide. So backscattering means that you have two vertices or 2 joints, and the microwaves are just going back and forth between these 2 points, and then they don't feel the chaoticity of the graph anymore. And these you can write down the trace formula for such systems. I mean, here I just use the exact result for the full quantum graph. And here I show the Fourier transform of the integrated spectral density. So the red one is the experimental eigenvalues, green one is theory, and one can see that this backscattering leads to slow oscillations, and these slow oscillations lead to deviations from predictions of random matrix theory, essentially. So these lead to non-universal contributions, and usually if you want to get a good agreement with random matrix theory, then you have to extract such contributions, which is impossible in quantum graphs, because they have too many of these. So that's a drawback of quantum graphs, but so one has always to fight with these disadvantages. But still it's a good system to study quantum chaos. Next slide. So we did several experiments in 2020. We just used a GSE quantum graph and changed the length of one of the bonds in each of the GUE graphs to still have a GSE graph. And we looked at properties for varying lengths. So it's a parametric system in a sense. And then you get it's called spaghetti's level dynamics, and you can also use these graphs to investigate random matrix predictions for such level dynamics. So this is on the next slide. I just show one example. One example is that you you always, when you have a chaotic system, then you always have points of close encounter, like I show in these blue circles. And you can compute the spacings at these points, and then you now compute the distributions, and you get for the experiment the red curves, and the black curves are the random-matic theory results for the unitary and symplectic ensemble. So agreement is quite good. And deviations are again attributed to these non-universal properties which can be extracted in this example. So in this case, they are not a big problem because you can simply extract them. So that's one example. Next. Another thing we studied that was in 2021, we looked at the statistical properties of a system. So when you do experiments, usually you cannot measure all eigenfrequencies. So you will have missing eigenfrequencies. And then you observe deviations from random-matic theory, because to obtain good agreement, you would need a complete sequence of eigenvalues. In the experiment, that's usually not possible to obtain them. But there are also random-matic theory predictions. So by Bodegas and Pato, they made predictions for the GOE, for orthogonal ensemble and unitary ensemble. We extended them to the symplectic ensemble and validated our random-matic predictions by using these experimental data. So on the right side, I show the results for the GSE. The blue lines are experiment, and the black dashed line is for our prediction for the ensemble. And on the left side, I show for the GUE case. So it works very well. And so that, yeah. Next slide. So here, we also did experiments last year on unidirectional graphs. That these are graphs where waves can only move in one direction, as shown in this one here. So they can only move, when they arrive at a vertex, they can only go out in two directions and come in two directions. So then you get a unidirectional graph, where waves can only move in one direction. And here I just show the scattering matrix measurements, where you just use this four joint here in the left and in the right, and they are close to 1 or close to 0.1 over square root of 2 if you choose as entrances 1 and 2 and as exits 3 and 4, and otherwise they are 0. So only along the red arrows they are non-zero, and otherwise they are 0. Next slide. So these are spectral properties for Gaussian unitary ensemble graph and unidirectional quantum graph. The idea was, if you use a unidirectional graph, that it means that you have waves that can only move in one direction, and then the prediction was that they behave like a system with violated time reversal invariance. So our idea was that this should be a better system than the GUE graphs, because there you don't have this backscattering. These are, essentially the vertices in the case of the unidirectional graph are reflectionless vertices, and so one doesn't expect any confinement to individual bonds, but we still see deviations, and the deviations are due to the fact that by only allowing one direction you get a loss of complexity, but you need a high complexity in order to simulate a chaotic graph. So that's next slide. So we also did simulation for quantum chaotic systems. You can also derive random-matic theory descriptions for the distribution of the scattering matrix elements. We derived exact distributions together with Santosh Kumar and Thomas Gur, and now we could use these systems to check them experimentally for systems with fully violated time reversal invariance. So the left part shows a GUE graph. So the red one curve is random-matic theory, the black one is experiment, and there we find a good agreement. On the other hand, for this unidirectional graph, we don't find good agreement for the transmission spectrum. That is, unidirectional graphs are not a perfect system to investigate properties of systems with time reversal invariance violation. So that was our result essentially. So next graph. So here I now just show another way to realize a quantum graph experimentally, and this is with a waveguide system. So these are very, so it will be published soon, this paper. So these are recent results from end of last year. So there we use a system which is constructed from rectangular waveguides. So rectangular waveguide, you always have a polarization in that direction, and in this direction we have only one electric field perpendicular to it, and then we obtain a one-dimensional wave propagation which corresponds to a quantum graph. I mean, the system solves a two-dimensional Helmholtz equation, and along the walls we have Dirichlet boundary conditions, that is, electric field strength has to vanish. And the wave numbers are, when you completely close this waveguide system, then the eigenfrequencies are quantized, and then you can obtain the longitudinal wave function. Wave numbers are obtained from there's a misprint, this should be an M from this is a quantization in this direction, and this is a quantization because you close your system. So you can get the eigenfrequencies by measuring resonance spectra like in a waveguide system, so one can study the spectral properties of such systems and compare again to random matrix theory. And it has another advantage because in this system you can also measure wave functions. Next one. Next slide. Oh, wow, that was quite fast.
Nodding.
This is okay, so then I first say something about the number of eigenvalues in certain frequency intervals. So the integrated spectral density in a quantum graph, it increases linearly with the wave number. In this case, it increases nearly linearly, as long as you remain in the range of a single transversal mode. So you can use, again, it's similar to a quantum graph as long as pi over omega is much smaller than km. So you get exactly the same result as for a quantum graph, as long as you don't go to the bend edges, essentially. And in that range, it simulates a quantum graph. So next slide. So, and as I said, the one big advantage of such systems is that you can also measure wave functions. I mean, in a microwave resonator, you can measure them by inserting a perturbation body. If you insert a perturbation body, then the frequency shift, according to Meyer-Slater, is proportional to the electric field intensity at the position. So if you want to obtain the electric field position, the intensity at each position, you just move this perturbation body along the waveguide system, and then you can determine it in each point. And here I show some results. So the electric field corresponds in a quantum system to the wave function, because you have this analogy between Helmholtz equation and Schrödinger equation, which is exact as long as you remain below in the range where the electric field is perpendicular to the top and bottom of the waveguide. And here I show some results. You can see that along each waveguide, it's a very simple wave, like we expect from the wave equation. I mean, it's just a combination of sinus functions. But when they meet at the vertices, then this leads to the complexity of the system. If you have bonds with an incommensurate length. So this is next slide. So there are also predictions for the distribution of electric field intensities of the wave function components. If you have a really chaotic system, it can be described by random waves. Okay, random waves. And the distribution should be Porter-Thomas. In a quantum graph, you see always deviations because the waves are, in some cases, clearly confined only in a part of a waveguide. So this is the same as in a microwave network, that you always find waves that are just moving along a fraction of the waveguides. And here you can see clear deviations from Porter-Thomas distribution, but this is in agreement with what one expects from the theory of quantum graphs. But here we show it experimentally for the first time, essentially. So next slide. And we also can, in such systems, violate time reversal invariance. In this case, we essentially introduce a magnetic potential by inserting a ferrite, and it's magnetized from outside, perpendicular to the plane, and then you get a system with partially violated time reversal invariance. So that's one of the disadvantages of waveguides, is that you can only partially violate time reversal invariance. Whereas in a microwave network, you fully violate it. But we derived random matrix predictions for this case, and I just show some results. And next slide. So for the spectral properties, there are also analytic results known for the case of partial time reversal invariance. Then you have to use a Hamiltonian, which is essentially, this is a real symmetric random matrix, which would correspond to time reversal invariance. And you add another term, so this makes the system Hermitian, and this part is responsible for time reversal invariance violation. When you choose psi with the square root of n over pi, then you have a Hermitian matrix, then you would have a GUE. So it interpolates between GOE and GUE, and results agree very well. So on the left side, we show comparison with the case of low ferrites. I mean, the blue dots are the experimental results for a waveguide graph, and the red lines are the results which are obtained by doing numerical computations for a quantum graph. On the right side, the blue dots are again the experimental results, and the red one is the random matrix theory prediction, essentially. So there we also find a good agreement. Next slide. We also looked at the system as a chaotic scattering system. For these cases, we derived analytic results, and here we compare them. So the black ones are experiment, red ones are the random matrix model, and I show results for the distribution of the reflection matrix and the transmission matrix for the case with no magnetic field and for the case with magnetic field. That is that such systems are also suitable to study quantum graphs experimentally, as long as you don't expect a quantum graph with fully violated time reversal invariance. So, and the advantage is that you can also measure wave functions. So that's next slide. So just conclusions. So I mean, it's now known since a long time. Since in 1999, quantum graphs were introduced, and since then, since 2004, experiments have been done, and now we did experiments with these microwave waveguides, and all these experiments show that quantum graphs are a suitable system to study properties of quantum chaotic systems. Also for open systems, that is for quantum chaotic scattering systems. And unidirectional graphs, one has to be careful because they, the complexity is reduced in such systems. And one of the drawbacks of all these systems is that you always have these contributions of non-universal properties. And now, currently, we work on a random matrix theory description for symplectic ensemble, which is not yet fully understood. So that's it. Thank you for your attention.
Thank you for the nice talk. Do you have a question?
Actually, I have two questions. So the first thing, what you did here is in quantum graph theory, one can use secular equation-based approach or scattering approach to analyze the spectral properties, right?
Yeah.
Both are presented in the
Exactly.
review paper of Santikos Kotos and Uzi Similansky. And then what here, as I understood, you are remaining within the scattering matrix approach, right?
Yes.
Not use a secular equation. And what is the second thing is if you compare in case of quantum billiard, where are you also well-known expert?
Yeah.
Quantum, I mean, spectral distribution is governed by the geometry of the billiard balls.
Yes.
Intuitively, one should expect that in the case of quantum graphs, the analog of billiard geometry should be quantum graph topology.
Yeah.
Like star graph or this complete graph, so on.
Exactly.
But in your results for the spectral statistics, it was not clear, at least for me, that did you consider topology dependence or dependence from the other parameters of graph?
Yeah, just, I mean, we always make sure that the lengths are incommensurate, and then, of course, you can vary the boundary conditions. So,
Well, boundary condition, actually, if you mean vertex boundary conditions,
yeah,
then of course, changing topology leads causes of changing of the vertex boundary conditions. In fact, so this is your analysis was on the by changing the boundary vertex boundary conditions. And second thing is when you make sticks or other words branching points.
yes.
There are several options. You can just directly stick, and then your quantum graph will be a uniform material, or you can put something for stick, special stick.
Yeah.
Then your uniformness will be violated by your vertex. Which case is true for your experiment?
Exactly. For the experiment with circulators, you have this problem. Because there you have the K-dependent vertex matrix. And also in the waveguide systems, you also have a K-dependent vertex scattering matrix. And there we had to, we designed an angle of 120 degrees to get a scattering matrix which is more or less homogeneous and doesn't change too much in a fixed frequency range. But also there, it's essentially not identical to a quantum graph.
The final question or comment. You have shown the waveguides, 2D waveguides, right? Or
yes.
3D waveguides.
Yes.
Actually, in quantum graph theory, we call it fat graph, or planar graphs. Or
yes.
Olaf Post and Paul Exner has.
I saw that they have a whole book, I think, on
yes, they have book
yes.
also on that. And what is important in this case, your system becomes not exactly solvable. You cannot solve as soon as you will include this transverse wave motion.
Yeah, exactly.
And then it's not possible to compute spectra neither by using this scattering approach or even a circular equation.
Exactly.
You cannot derive.
Yeah.
So how is your strategy to compute spectral prediction for that?
So we only use, in these experiments I only showed results for the one-dimensional case where you have exactly one mode.
I see, not branching.
Yeah.
I see.
But we also went above this frequency, and there we just looked at the experimental result and used COMSOL to get theory. And there's now a recent paper by Knutsman and Smilansky who consider also the case where you don't have more than one mode, transversal mode essentially excited. So in this we are still looking at.
Yeah, any more questions? Yeah, I have a simple question. How can you realize the unique directional in experiment?
They use, it's called hybrid. So there's a company that constructs such 4 joints.
A joint?
Yeah, these are 4 joints, so you usually use T-joints, and these T-joints, the common one, you just obey Neumann boundary conditions. And there we found a company they are able to construct, but they don't want to tell us how they do it.
Yeah, it's very good.
Actually, in my talk I'm going to present one of the schemes for realization of this reflectionless unidirectional graph. I will also, my presentation is related to that also.
Very good.
Yeah, any more questions?